This conference will now be recorded.
Okay. Let's just give a minute, Rochelle, then we will start now. Okay, it is exactly 1 o'clock, depending on where you're sitting around the planet, but where we are in South Africa is 1 o'clock in the afternoon. Time for us to start with today's webinar. Thanks, Rochelle. I realized that you started recording the webinar. Thank you so much. So, good afternoon, everyone. Welcome to yet another NICOLA webinar. Kindly allow me to introduce myself as your host for today. My name is Christina Masimula. I work for Shell as the Soil and Groundwater Senior Program Manager. I am based in the Johannesburg offices of Shell. Yeah, that's my day job. My voluntary job is that of sitting in the NICOLA Steering Committee, and I occupy the position of the chairperson of NICOLA. It gives me such a great pleasure to be hosting you all today. We are happy to be hosting Dr. John Saul from Columbia Technologies to spoil us, literally to spoil us with some knowledge, experience. He gathered over 35 years of his career. I will be handing over to him in a moment, but before I do that, allow me to still few minutes of his time to go through some few points or other formalities as we normally do in webinars like this. Rochelle, if we can move to the HSSE slide. Yeah, so colleagues, as usual, when we do webinars like this, we do start with an HSSE moment. We continue to be working under severe constraints of COVID-19, and we're getting used to this new normal of doing work under the controlled measures due to the pandemic. As we continue being out in the field to do the work, I would like to remind ourselves to maintain our focus on PPE. Let's take a moment during our toolbox talks to emphasize the need of wearing appropriate PPE and making sure that PPE used during the works is within the expiry dates, it's fit for purpose, it fits correctly, and people are actually properly trained on how to inspect and use the specific PPE. This is indeed an acknowledgement that regular PPE requirements might be slightly different in light of what we're observing under the COVID-19. We move to slide number 3. Rochelle, yeah, that one. So, colleagues, for those of you who are new on the call, they haven't joined any event organized by NICOLA, I'm giving you a very special welcome and hope that you will find the webinar today to be very informative and exciting. And we hope that you will join us again in the next or rather future webinars. Some few reminders on NICOLA. NICOLA, as we know, it stands for Network of Industrially Contaminated Land in Africa. It was established in 2014. It was established as a copy of the successful NICOLE, note E at the end, which stands for Europe, Network of Industrially Contaminated Land in Europe. NICOLA was basically established to proactively empower the African contaminated land management sector to identify and manage contaminated land within a science-based, sustainable, best practice frameworks. How we do this, we do it through 3 main themes, through knowledge sharing, through networking and emphasizing scientific best practices. In terms of the knowledge sharing, what we do is we have established different forums to address this. We have established working groups to work on a number of emerging technical issues in the field. We have ordinary members of the NICOLA volunteering and sitting in these working groups, serving us with their knowledge. Also, we have a number of NICOLA members developing and delivering training on a number of technical topics. We also hold an annual face-to-face conference, but unfortunately, due to the current pandemic, our 2020 conference has been postponed to 2021. In terms of networking, we continue to embed our relationship within the network. We have regular social events. Obviously, we are not having any of those now for obvious reasons, but we are hoping to continue with these sessions again in the future. Lastly, for our inspiring scientific best practices, we are stimulating our coordinating interdisciplinary projects on collaborative problems-oriented research and knowledge transfer identified needs. Something extremely very special to NICOLA to celebrate its efforts was presented by the Department of Environmental Affairs last year when we were awarded to be the winner for contributing to land remediation in Africa. And we really share this award with all our NICOLA members. If we'll move to slide number 4 quickly, Rochelle, a quick one, like I mentioned earlier on, that we have annual face-to-face conference, which the 2020 is not happening because of obvious reasons, where we are pushing it to 2021, but we are delighted that when we do that, it's going to happen concurrently with the SASTREM. We are delighted to be co-hosting the 2021 Global SASTREM Conference in collaboration with the Department of Environmental Affairs. The dates as presented on the slides, the 28th to the 29th of October, we've identified the venue to be the Spear Wine Farm in Cape Town. Look out for further communication around this from the NICOLA Steering Committee for any information as a build-up towards the conference. Last slide from me, Rochelle, is to also communicate the upcoming events. We are delighted that we are going to be hosting Simon Lawrence from SRK on the 29th of July, time 12 o'clock, to address us, or rather come talk to us about the near surface contaminant transport predictions by combining hydropodology and finite elements simulation. Last one that we also delighted is that, through our great collaboration with the DEFF, we've managed to secure Dr. Mpochitangoni, the director of land remediation from the DEFF, to come and address us for an hour to tell us the government's response to contaminated land during the COVID-19. Please look out for further communications around this, because I believe there's pre-work that the steering committee is wanting, especially with the webinar with Dr. Mpo. So, colleagues, with that, allow me to formally call on Dr. John Saul to address us. Unfortunately, it's not going to be a conversation where we allow questions while he's talking, but I do encourage that as he's talking and you've got a comment or other question, do use the comments field on the webinar and address your comments and questions there. When he's done with this presentation, I will be picking up comments and questions and we address them back to him. Dr. Saul, thank you so much for borrowing us your time to come talk to us. Dr. Saul is a co-founder of Columbia Technologies. He brings to his role as president and CEO 35 years of experience directing the development of innovative business solutions, focusing science and technology to advance the state of the environmental services. At Columbia, John is responsible for the overall direction of corporate activities, the quality of the company's field services, and business development. He's also co-founder of the award-winning Smart Data Solution, real-time data service platform, and has played an integral part in providing clients with real-time decision-making information. A former officer in the U.S. Navy Nuclear Submarine Force, John holds a BSc in engineering from the United States Naval Academy and an MBA from Chaminade University of Honolulu. He is a member of the Small Environmental Business Action Coalition, the Sustainable Remediation Forum, the Society of American Military Engineers, and the National Groundwater Association. Wow, such experience, Dr. Saul. Please bless us. Over to you.
Many thanks, Christina, and good afternoon to everyone. Thank you for attending. And I appreciate the promotion to doctorate, but I'm still working on that element of it. So I'm joining you this afternoon from just outside Washington, D.C. And I'd like to salute NICOLA for how pressing forward with this educational series that you're doing through these trying times. It's really impressive. And I do hope everyone in attendance that you and your family and your friends are doing well amidst the crisis. A special thanks to Dr. Steve Kaluli with USK Environmental for his support as both my partner and collaborator on this presentation. My goal this afternoon is to report our observation at looking at a fairly large number of these former or active retail service stations here in the United States. And the hope is that our observations will help you bypass many of the lessons learned, expensive lessons learned over the last several decades here in the United States. So I'm going to cover this afternoon, excuse me, sort of a brief synopsis of our program, just to give sort of a context to what we're talking about. Introduce our concept of LNAPL 3 and site management, which is a parallel document to several other around the globe. Give you the results of our investigations, some couple of case examples of what I'm talking about, and maybe some thoughts and metrics for sustainable long-term management. So our world started way back in the early 1900s with the advent of the automobile and America's love of the vehicle and the way to get around. And it continued to expand over the decades. And in the 50s, post World War II, a huge national network of highways were created, both for commerce and supposed security. And that really generated literally hundreds of thousands, if not millions, of these retail gas stations across the countryside, many in rural areas. And, you know, as you all know, they all had underground storage tanks, and in the early tank technologies, all of them leaked. And we really didn't deal with that in those days because it was basically a decision Do I need to worry about this? Is it bothering anyone? Or what are the economics of just keeping it going on the path that we're doing now? So that was sort of the mentality through the 50s and early 60s here in this country. And then in 62, sort of a watershed event, literally with Rachel Carson's book on Silent Spring, started to change the awareness of what was going on about the environment here and around the world. And then in 69, things like the Cuyahoga River fire and really brought a strong emphasis, and this was all getting to the post-Vietnam era war, where there's just a whole lot of awareness of what's going on with government and what's happening, and that generated our Clean Water Act in 1962, or 72, excuse me. And this is when the balance shifted, when the regulations then basically required the owners to understand the horizontal and lateral extent of contamination, and if possible, get it out of the ground, remove it as practically. And so that started basically created an industry of what's going on around these underground storage tanks, which were in every state across the country. Everyone was affected. Many of them were impacting rural groundwater supplies, and you may not know, but a lot of our drinking water still comes from the underground aquifers across our wide land. It further evolved, and then our underground storage tank program was created as an outgrowth of the Clean Water Act in 1984. And because we had all these cars running around everywhere, they figured out they could fund this by charging taxes at the pump, and started tackling, what are the best practices and how do we go out and tackle it. You have to check the mutes here.
Yeah. Thank you.
Okay. So over the period of time now, for 30 plus years, we've closed close to 2 million tanks across the country. In today's program, we have a little over 500,000 of active tanks and approximately 200,000 sites that are under the regulated program. And this funding support and whatnot only applies to tanks that are fully, involved or in compliance with the regulated program. But we still have close to 64,000 active releases as of spring of this year. Kind of give you a flavor of what those tanks look like, I go back to 2014 when a national backlog study was done. And we found at that time a large portion of the sites were in, what you would call the more populated states. But some of the surprising facts were, close to half of them were very old, and that continues to this day. Greater than 15, but we're seeing 20 and 25-year-old sites, including ones that are considered high priority, which means they are in places with receptors that need to be taken into account. Less than half had not begun some sort of remediation. About a quarter of them had not even been characterized, and a large portion of them, and I would tend to say probably more than 78% from our findings, had impacts to groundwater. And so the problems continue to exist. It is typically an old problem, and it does impact groundwater. So in mid-year, spring of this year, we're still just under 68,000 open cases, despite an aggressive program to go after that, which is distributed throughout our 50 states. And so how are we doing, after this 30-year effort? Well, the number of cases is going sideways. Essentially, we're resolving about the same number that we're creating every year, or reporting under the regulated program. But more significantly, the life cycle cost of dealing with a site is going up dramatically, and the age continues to get older and older and older. So the problem's not going away and it's getting more expensive. And so to me, that's the definition of non-sustainable. Economically, it's not sustainable, and environmentally, it's not sustainable. And so if you look at any site, at what goes on out there, you see this unsustainable cost curve growing. And so it's it would be nice if you could almost program it like that, but the trouble is it does something more like this, where it's back and forth and back and forth. We think we have it, then we put in a remediation system, and then we take it back out, and then we get rebound, then we have to go back in and put another remediation system in, and then take it out and put a rebound in it. And so we have a very unpredictable cost curve. So from anybody who's in portfolio management or budget management, that's a very difficult thing to deal with. In 2000s, our group, we call it the Interstate Technology and Regulatory Council, formed and started looking at best practices. And we went through what we call LNAPL 1, LNAPL 2, and now LNAPL 3, which is really how to manage on a long-term basis like non-aqueous phase liquids or LNAPL sites, and really started looking at it from, well, what are the best practices? And this guide can be found in the US, it can be found in Europe, and found in Australia, there's many different sources for this, but it really looked at what do we need to know about these sites, and what's the reality about what we're going to be able to do with them, and what's the role of natural source zone depletion in there. And we've heard some of that already this year or this season in the training sessions. And so if we've done all these sites, we asked ourselves, well, what's the rubric? I mean, what do we need to know? And this is a very busy slide, but basically it says, well, what's the history of the site? Where is the LNAPL? What soil is it in? Is it transmissive, or can we recover it? What's the impact or the relationship of that in the groundwater? Is it perched? Is it confined? Is it unconfined? Do we have dissolved phase plume considerations? Are there any vapor intrusion issues? What do we have out there in terms of hardware, and is it aligned properly with both the LNAPL as well as the permeability and the water? And what is this stuff about this natural source on depletion, and how can we use that? And then what else do we need to know to inform our management or remedial technology selection? And so we said, well, you know, we're doing a lot of these sites. What do we know about our universe of sites? And so we said, you know, I bet we've done a bunch of them. And I went back and we looked and we said we've done about 150 of them in 5 years. We actually counted it up. We're now at 170. And using numbers from our regulatory folks, you know, it comes out to about R500,000 per site in terms of an investigation, doing these high resolution site characterizations, or what I call focused investigations. And in many cases, they made the decision that said that better information is worth not running an O&M system, running the O&M on a system for a quarter or a half a year. And so rather than continue to pump without recoverability, let's stop and figure out what we really have, and say take that money and apply it to a better assessment or diagnostic of the site. And so that's what begat the initiative that we took on, and the Federal Office of Underground Storage Tanks asked us to report back on that, and this is sort of the summary of that work. And so taking the guidelines out of LNAPL 3, it turns out, I mean, we felt we needed to look at multiple components out there, and you need to understand what chemistry you're talking about. And so much of the chemistry that's collected is really risk parameters. Let's look at BTEX, let's look at naphthalene, maybe we look at lead components, but we're really not looking at the total mass that we're trying to take care of. We need to look at the soil. It's highly variable, highly heterogeneous. We need to look at the relationship of the LNAPL to the groundwater, because that can drive LNAPL in places that we weren't expecting. And we mentioned before, we need to look at dissolve phase. Is there a vapor phase issue? And then what we learned a lot from the vapor phase is that there's a tremendous amount of natural degradation going on in the vapor phase processes at that air-water interface. And then what I call the low-hanging fruit, what we found was a significant number of sites had a misalignment of what we were using for sources of data, these long screen monitoring wells, versus what the actual situation was in the subsurface. And there's a huge misalignment between the screen interval, where the LNAPL is, where the permeability is, how the water would get to the screen. And remember that the screen is measuring a dissolve phase component usually, and that's a small percentage of the total mass that we're trying to manage and take care of. And so the preliminary findings that we reported back to the government, from 150 sites, kind of read like this. There were significant gaps in the existing conceptual site models. Basically, we didn't know where the LNAPL was. We didn't know what soil it was in. We didn't know its relationship to the water, and the monitoring wells or recovery wells were typically not in the right places. And this is after having spent, on the order of $5 million ran on these types of sites. We were real good with air sparging in the early days of cleaning up the vadose zones, but what I think we saw presented here a couple of weeks ago is really an iceberg effect. The majority of the residual LNAPL is below that air-water interface, and therefore it's in a saturated soil regime, and we really have to tune our technologies and our data collection to look at that in that equilibrium state down below the water level. Stratigraphy is much more complex than is perceived or displayed or reported in many of the reports, boring logs, conceptual site models that we looked at. And almost always the residual product that's there is retained in tighter soil components, which makes sense. And it's the water coming by those tight zones that become contaminated that then become our issue because we have this water focus. Many of the sites, well, a small number of the sites that we looked at that had chemical injections as a remedial technology generally did not reach the tighter LNAPL in the tighter zones. And it was two issues. One is the LNAPL wasn't identified there, or two, the basic pressure relationships of trying to get that chemical in contact with the LNAPL is a difficult challenge, and you've heard that discussed here. Probably most disconcerting, or the bad news, was oftentimes efforts for vacuum extraction resulted in a redistribution of the LNAPL. It was sometimes pulled from shallow to deep, pulled past a retaining layer, pulled down a well screen, pulled down a well filter pack into areas, and then created essentially a problem that was worse than the original spill. And I mentioned already the misalignment of the LNAPL with the recovery wells and the fact that it's bound up in these tighter layers. So we found essentially a lot of mass out there in places that people weren't expecting it. Most significantly, that mass was not recoverable. All the concentrations that we measured with detailed high resolution sampling, none of them in the mass of the body of the LNAPL body exceeded the screening values for recoverability. There might be mobile product within the footprint of the LNAPL that you might find in a well, and hence we get some products in our wells, but that product was not recoverable much beyond a few centimeters, maybe a meter or two from that well. And it was localized within the plume or within the body, but not at the edges of the body. The bodies with any age have reached equilibrium with the environment, particularly the water pressures, and have been acted upon by the biologics and become in a very disassociated mass, so that the concentrations and saturation levels are such that it really won't support recoverability. So why does this situation exist? We started asking ourselves, and our contention is that so much of the regulations, so much of the practices or prescriptive work plans that we started the program with have a blinding focus on groundwater. What's the concentration in the water in the well? What's the concentration down gradient? What's the concentration in the sentinel well? What's the impact of the receptors? And so we focus on groundwater and its numbers. In reality, the mass is in the soil. And if we don't go back and look at the LNAPL and its relationship with the soil and the soil permeability characteristics, we're really not going to find the 90+% of the mass that we're really trying to deal with when we put some sort of fluid recovery system down there or chemical injection or whatever. So that was the first sort of misdirection in the pathway to clean up that we saw. And here's a simple case example. We actually just finished this report yesterday of a project we were doing last week. You see in the picture, we're using a combination of technologies here, the optical imaging profiler, which is a fluorescence tool that gives us where is the actual residual product in the pore spaces, and then we're using membrane interface probe, and both of them have hydraulic profiling on it. And so the monitoring well network and the dissolve phase was the focus of attention, which is typical. You go to most of these sites and there's an extensive groundwater monitoring network in the perceived direction of the local gradient. And in fact, what's missed is the huge amount of residual product that still sits on a site. So this site is 15 to 20 years old. It's had millions of rand of remedial technologies thrown at it, and yet here we are going in there and finding a lot of product. And this shows you the high pressure zones or the tighter soils, and the product is up underneath all of that. And so you've got a very stratified environment there. And if we look at that, just looking at it across the cross section, you can see the air water interfaces coming across here. You see all this tight material up in here. Then we have this wonderful sparging network that was put in, but look at the vertical relationship between the sparge points and the residual product. Essentially, we missed the target in putting that network in because we didn't understand where the target was when we built that. So that's a classic case that we see out there where the LNAPL wasn't defined because we're trying to define the LNAPL using groundwater monitoring wells and a dissolved phase concentration, which is not really giving us the answer of the actual LNAPL material. Same sort of example here. This was a site early on. The underground storage tanks were removed from the tank enclosure here. A monitoring well network was placed in the up gradient and down gradient paths, and then way down here to the southwest, fumes started showing up in buildings, storm drains and things of that sort, which indicated there was a bigger problem. We went back and once again found a considerable amount of LNAPL mass in a different section of the property. And again, that mass is what's going to lead to this down gradient dissolve phase plume. And so if we don't take care of this issue, which again, I say from what our data says is not really fluid recovery, we're going to continue to have this dissolve phase and then potentially vapor phase issues. So that was a pretty common theme that we found across the site. And so the sort of the first lesson learned is that risk measurements of BTEX, naphthalines, various components are not remediation parameters. And if we're going to do an assessment to come up with a long-term sustainable solution, we really have to look at mass, volume, chemical composition of what the material is in the soil itself, and I should say in the saturated soil. We're going to have to understand the characteristics of that soil. We heard some presentations here in the last few weeks about the transmissivity of the LNAPL. Early on in a release, the transmissivity may be sufficient to actually recover product, but once your skimmers stop working and once you reach a certain age, it has been biologically disassociated to the degree that it's not going to recover. But it will continue to impact the groundwater. And so at that point in time, we really kind of need to look at what are our other options, including natural source zone depletion. And we saw this curve essentially, recoverability goes down with time and with product thickness as it's disassociated. And so we really need to look at what kind of treatment or treatment chains that we can use. And this is from LNAPL 3, and sort of summarizing, well, what's the concern? What technologies do we have for recovery, and what's the potential for recoverability? And they use 3 basic states of definition in LNAPL 3. It's migrating LNAPL, which means it is actually moving beyond its footprint. It's mobile within the footprint. It's the footprint stable, but it's mobile within it. And this is what you will see when you have a product in your wells, but you're not moving product beyond the site boundaries or beyond the plume boundaries. Or it's become a residual mass becoming disassociated, and we have 3 different levels of disassociation, but our recoverability and transmissivity is well under 0.8, I'll use the term square feet per day. And at that point in time, mass control, mass recovery are not really possible. We're down into somehow we have to change the phase of that material, either chemically, thermally, or take advantage of natural source zone depletion. And so if we think about something sustainable, putting all the hardware in the ground up in these stages, that's not going to work once we get out into these years. And before we put this hardware in the ground, we better understand what these conditions are before we put it out there. And studies that have looked at natural source zone depletion versus active remediation systems find that natural source zone depletion is as good as the average of the mechanical systems and fluid recovery systems that are out there. So it continues to, armed with that, we then looked at another site and said, well, let's go in and look at a more in-depth look at metrics on a site. And we went back to another site where the tanks had been removed many, many years ago. And you can see that in the tank enclosure, they left 10,000 milligrams of per kilogram of oil in the walls or the base of the tank enclosure. It was backfilled with riprap and whatnot. So we've done tank removal, we've done soil removal. Air sparging and vapor extraction were then applied to the enclosure area, and then followed on with chemical injections. So we again have put 5 million Rand into this project and still have a dissolved phase plume down gradient. So we went in to look at that, and adjacent to the tank enclosure, which is here, we found a considerable amount of mass, again adjacent in the adjacent property to the tank enclosure, which then basically fed the dissolved phase plume. But then we looked at, you could pretty well map the dissolved phase plume in high resolution, determine the pathway that was being generated, and confirm the permeability pathway. And then we looked at, well, you can actually go in and look at the metrics of the groundwater coming into the LNAPL body, exiting the LNAPL body, and recovering down gradient. And so you can look at the natural degradation parameters, and you can look at the natural source zone depletion rates based on CO2 parameters, and you can basically come up with a set of metrics that say, yes, we have LNAPL here. Yes, it's creating a dissolved phase plume, but yes, we have metrics where we can monitor the performance of what's going on. And yes, it's cleaning the site up at least as effectively, if not more effectively, than something else we can put in from a mechanical fluid recovery system. So this case basically was able to make the point to the regulators that further remediation of this was not going to be cost effective. And in fact, we could safely monitor the natural processes and if necessary, enhance them for a more sustainable long-term solution. And if you look at that, in 3 dimensions, which is a lot easier to do these days. Let's see if we can pull that up real quick. Loading. You can see that residual LNAPL there. You can see it, the dissolved phase come off of that residual LNAPL, and then you can monitor the dissolved phase plume as you go down gradient with that. And so the key to getting that mapped out and understanding what you have is a high resolution amount of saturated soil sampling and high resolution groundwater sampling, and then you can put that map together pretty clearly. So it's about the detail of the high resolution that becomes critical in doing this and understanding that you're really looking below that air-water interface. So let me see if I can find my way back to my presentation. So the concept behind the high resolution assessment early on is to look at characterizing better early on so you can monetize possible options based on the condition of the LNAPL, the size and location of the LNAPL, and the soils, and create options that are more sustainable going forward. In order to do that, my message is this: you have to be systematic. You can't, which means you have to be systematic in your measuring process for whatever technology you use. It has to have sufficient data density to do it. ITRC LNAPL 3 gives you some guidelines. There are other guides that do that also. And if you're not systematic, you will miss a large portion of the total mass that's there and affecting the behavior of what you're doing. And if you don't do that, you're going to waste a lot of money during this life cycle of cleanup and LNAPL management. So being thorough. Again, I pull this from LNAPL 3. Now that we know where the LNAPL is, we know what soil conditions it is, we know what the condition of the LNAPL is, we know what constituents are in their state of degradation. There are a number of performance metrics that you could put on the site to say we're meeting desired goals or we're not meeting desired goals. And that comes to the reality of this. Once the site has some age to it and stability to it, you now have essentially 3 options. You need to remove it, physically, chemically transform it, or phase change it somehow, or you have to basically come to the conclusion you're going to coexist with the groundwater contamination and figure out how to monitor it and control it, or you need to enhance or pursue further natural degradation if you want to speed the process up. But physical recovery is going to be very, fluid recovery is going to be very difficult. And from a portfolio perspective, there's going to be an unpredictable number of sites that basically get out of the box, as I call it, and they're going to significantly upset your budget, and they're going to end up costing tens of millions of rand. We have many of these sites we looked at were over $2 million US, and you do the translation, you're into tens of millions of rand, and that's going to affect your budget. It's going to affect your promotion and turn the organization, and then, quite frankly, affect your ability to get rehired to take a look at the site, because they're going to say, well, let's hire somebody else. And the third reality is, if you talk yourself into pursuing active remediation without thoroughly understanding that conceptual site model early, and including the LNAPL and the soil stratigraphy, you're going to be gambling on the long-term life cycle. And it may fit this year's budget, but in the long term, you're essentially going to you're turning the money over and draining it down a long pipe of remediation. So our recommendations are: get a conceptual site model, upgrade what you have, look at some systematic implementation, LNAPL 3, other documentation that are out there. Look at things in high resolution, and that's not tools, that's measurement distances and locations. So you can use sampling, you can use tools, you can use direct sensors. We like to use all of them, but do it early before you start down the expensive remediation path. I think last presentation we saw the gent that presented on what am I trying to think of? Guaranteed fixed price to clean up the site. The first thing they did was go in and look at it in high resolution to make sure they understand that. You've got to look at saturated soil sampling and the protocols. You need to look at the total hydrocarbon mass, and we strongly recommend pursuing the more economical and sustainable natural source on depletion parameters and taking a look at that. So I'm going to stop there, Christina and Rochelle, and see if there's any questions. So thank you very much.
Thank you so much, John, for a very knowledge sharing and informative session you just did with us. I have no doubt we will have questions from the attendees. I mean, one thing that I took from the presentation is that we need to acknowledge that we're living in a digitalized world, and we need to use technology to help us make critical decisions before we spend money. So thank you so much. Before I am going to open up for questions, Rochelle, can we do?
This conference will now be recorded.
Okay, great. So before I open up for whoever has a question to unmute him or herself to ask, I will take the first question that I see on the comment box from Daniel. He's asking if attendees will have access to the presentation at the end of the webinar. The answer is yes. What we are doing, hence the session has been recorded, that at the end of the session, we are going to share the recording with the attendees. So the answer is yes. Can I then open up for anyone on the line to unmute if he or she has questions to John? Any questions?
Yeah, good day everyone. Thank you to John for the section. I just want to ask if I was wondering if you have the guys that worked with EKG, electrokinetic statistics implementation solution, and what is your view in terms of future prospect in utilizing that in African projects? Yeah, that's one thing I just need more facts on. Thank you.
John, I didn't get the question. The line was not that clear. Did you get it?
I'm in the same situation. I didn't quite get the question.
Okay.
Daniel, the line was not.
Okay,
let's try.
Perhaps he could write it in the chat window.
Yeah.
Okay. Let me do that.
Yeah, let's do that. Okay, while we're waiting for Daniel to write up the question, can I go back online and check if anyone else has a question? It doesn't look like we do have more questions online. Daniel, can I check if you are typing in your question on the comment box?
Yes, I'm doing that now.
Okay, cool. Let's just give Daniel a second, John. There we go, John. What is the prospect and challenges of electrokinetic geosynthetics in brackets EKG and remediation projects?
Daniel, thanks for the question, but I am not a remediation guy, so I really don't look at the effectiveness of those different techniques. I know that it is gaining a lot of interest around the globe, and I encourage everyone to look at different alternatives because I think our old methods have reached the limit of their capabilities. Our focus is really to say more of the diagnostics to say, hey, doctor, here's where your problem is, and this is the kind of problem you have, and the treatments that you've got in place are not working. So we're really about the data gathering and presentation of that information about what the reality is more than we are about what you should do about it. So, though I do have a bias towards natural, economically sustainable cleanups, if that wasn't obvious.
Yeah. Okay. Thanks, Jen, for that. Can I open up and check if we've got somebody who wants to ask? I guess it's the last chance. It doesn't look like we do have more questions. John,
I have
let me
not
join.
stimulated discussion.
You did.
Or
You
everybody's
did.
ready for lunch, one or the other.
Yeah, it means your message was very clear, hey? You stimulated everybody's brains quite clear that you delivered the message. Thank you so much. Okay, we've got Adolf. Adolf October. The question is, what are some of the important metrics to look at for dissolved phase plume migration and recovery?
Okay, so two components there is the dissolve phase migration, and the second is the recoverability of that. So the dissolve phase migration and the recovery are going to both be driven heavily by the permeability profile of the soil. There will be preferential pathways, and the important component is identifying those pathways and then aligning both any monitoring and recovery systems to the pathway. And what you will find in any given transect of a site, that 80 or 90% of the mass transfer or migration that you're talking about occurs in only about 10 to 20% of the total transect. So remember, most of the body, LNAPL body, is tied up in tighter non-permeable soils, but there will be a leakage path or a hole in that wall, and that's where the migration will occur, which will have a significant impact on your risk assessment, because if you've got most of the mass going through a small hole with a higher flow rate, that's going to travel further and not a straight line for that matter. So the most important metric, in my opinion, for dissolved phase plume migration and recovery is the soil and the soil permeability characteristics. You've got to understand those, otherwise you're not recovering mass. After that, you can look at the chemical parameters, both redox parameters and constituent parameters, and again, to profile that across that permeable zone.
Okay, great. Thanks for that question, Adolf. One last chance. Let me check if we do have any further questions or comments. Okay, I will close it there. John, thank you so much.
Sorry, Christina, there's two more comments in the chat box.
Okay. Oh, okay. There's one. Sorry, I missed it.
Yeah, that's okay.
The one from Michael Maluleke. For your model to be successful, is there any number of boreholes required?
The number of boreholes is highly variable. It needs to be driven by the site data, and it needs to be systematic. And so the size of the site will drive that. The tightness of the soil will drive more borings than fewer. Boundary conditions of the body, LNAPL body, and then whether you're looking at dissolve phase or not. But if you just focus on the LNAPL body, again, you've got to get it bounded in all directions. But most important is the resolution. Equally important, I guess, is the resolution vertically. There's highly variable conditions in that soil going down vertically. And so that's where the resolution really needs to be focused on. Don't think about how many holes in the ground I want to put. Think about how many samples you want to take out of that hole and what scale of measurements appropriate for the thickness that you're working with to get a representative understanding of that mass and soil conditions. So think about resolution vertically, which is where most of the error occurs. Sometimes they just completely miss masses, as I demonstrated in the presentation. But think about how many do I need vertically, no matter what kind of soil you're in, whether it's consolidated or unconsolidated. You're going to need a profile that gives you the answer to that total mass situation.
Great. Rochelle, did I take all the questions on the chat box? I think I did, yeah?
Sorry, there's one more from Ernst or Ernest, just above Michael's.
Okay, I don't see it. I see Michael, there's Adolf, there's Gloria.
Just below.
Okay.
Adolf,
are you seeing it? Can you please respond?
Yes. The question is from the 150 site, what has been the success rate? On hindsight, anything you think could have been done differently in approaching such problem?
Yeah, so the common characteristic of all 150 sites is they all failed. And they all still are spending money trying to achieve a goal which in the current process is not achievable. And so where they went off the rails is they didn't have a conceptual site model that understood where the LNAPL body was when they started, and then they continued down a pathway of remedial technologies and approaches, which sometimes had some effect, but in many times made it worse. And they have not addressed the residual product in a manner that now, in its state of degradation and disassociation, the current methodologies won't take care of that. So now they're going to have to go through a phase change or reorient the thinking to how do we live with a groundwater problem and how do we control or manage that? Or they have to remove the mass some other way.
Wonderful. John, thank you so much for borrowing us your time this afternoon to share your knowledge with us. I think everybody on the call will agree with me that the session was very informative and we found it to be very useful. Thank you so much to everybody who also made time this afternoon to join us. Really appreciate it. Like I mentioned earlier on, look out for more webinars in the future. Thank you all. Go well. Have a great and safe afternoon. Thank you all. Bye.
All right. Thank you all. Take care. Be safe. Be well.
All
Thanks,
right.
John.
Sure.
Thank
Thanks,
you.
Christina.
Bye.
Thank you.